So I'll talk about some older and more recent work with a number of people about machine learning and meaningful games, the Hamilton-Jacobi equations. So of course, all of you are aware of this. My interest is not so much in images or in language, but it's more in my personal interest is in using generative methods and machine learning methods in science problems. And we'll see some of them towards the end. A lot of ongoing interest, of course, right, in scientific applications. So just a quick primer, right? A very quick primer on what is generative modeling. Just some of the fundamental objects that come in. So it's a great topic for our students that like probability theory, right? So the idea is that you are given some, as Luke said, mythical distribution pi of x, that it doesn't exist, you don't know it, and you know it only from data. And you want to approximate it with some family of models, and then if this is a nice family, you can sample very quickly and generate new samples. So for example, if you have a library of molecules and you discover new molecules, discovery of new molecules for what your favorite application, maybe that's a way to do it, right? So you have, as in standard statistics, right, you have a parametric families, but the way we build the parametric families, this is where deep learning comes into the game, and neural networks and transformers and all that stuff, right? So we have new, very important ways to parameterize probability distributions. And once we have a nice parametric family, then we have to decide which one is the closest to my data, right? Which one from my family is close to my data. So I need the concept of distance. So I need some type of distance between probabilities, right? And this distance between probabilities should be strong enough and good enough to deal with data, right? Because I don't have the formula for pi of x, right? So we need a way to to parameterize, and we need a way to measure distance. So we'll need something from what? Maybe information theory, maybe from optimal transport, maybe from something, right? And once you find the best one, you'll say, oh, well, okay, that's going to be my approximation. Maybe I'll declare victory, mission accomplished, and move on, or maybe not, right? How do we do it? How do we set up the problem? There are two fundamental things here that we teach to our undergrad. I teach to my undergrad students, right? My undergrad probability. So one of the things that we teach our undergrad probability classes is the method of transformations. You take one distribution here, right, and you transform it to another, right? So when we teach this to undergrads, you take a Gaussian, you transform it to another Gaussian, or a uniform to an exponential, or something like that, right? So I want to transform something. So the idea here is I'm going to build the parametric family, right? A parametric family. So I have a distribution here, a very simple distribution, and I want to transform it towards my data distribution, and I want to find the best transformation that's going to do that. It's going to approximate my target. So this direction, so once I have this perfect distribution, right, that's my generative model. So this is my forward direction. So I want to point out this fundamental idea. Forward direction, backwards direction, right? So the backwards direction is what? Well, remember in that probability class, right, undergrad probability class, you learn about this formula, right? How to go back and forth between the two probabilities, right? Change of variables, right? Change of variables, right? Calculus 3, right? So here it is, right? So that's the inverse, right? So this is f, that's the inverse, right? That's why we call this the backwards direction. So we have this formula, and then we have to realize who's the closest to this. So in the backwards direction, you have to minimize some distance from the data, and usually you use maybe maximum likelihood, and maximum likelihood, as you know, is KL, Kullback library in disguise, right? Right? So with the backwards direction, we learn, and with the forward, the generative model, and the forward direction, we just generate, right? So, right. So that is at the undergrad level, right? So now at the cutting edge research level, you have to understand how to do this, right? How you're going to build this object, right? And in practice, these types of transformations, right, can be very deep, right? Can be very deep. So it could be a composition of many transformations. So what you see here is what is called the normalizing flow, right? Discrete normalizing flow. So it can be very deep. How deep? Super deep, right? So in this paper that has the most citations in the 21st century, right? The ResNet paper, right, is, I don't know, 100,000, 200,000, it doesn't matter, right? The order of magnitude matters, right? So, right, they built the first super deep networks, right? And of course, neural ODs, we've heard a lot about it, right? It's a continuous version of that, right? And of course, lately people are doing transformers and all that, right? Very deep, or fairly deep things, right? And all that, right? Because of the depth, you see here, what do you see? You see a flow, right? You see a flow. So a flow, this flow, as you know, so most of you, many of you are applied mathematicians, you think of transport, ODs, PDs, whatever, right? Yes, so the depth means, right, that you have to do some type of flow, some type of dynamical system, right? So state of the art, generative models are flows, right? So this is a normalizing flow, right? From a normal distribution to the target. Again, back and forth is needed. Another one here is diffusion, right? Score-based models, right? Again, we saw in Sitting's talk a detailed analysis of this, right? And other talks popped up many places, right? So that's an OD, that's an SD, right? And of course, there are more recent developments, right? Flow matching, whatever, right? Ongoing, right? Some commercial products, right? And yeah. So preview of part of my talk is that all these things are secretly solving Hamilton-Jacobi equations, doing control, doing midfield games, stuff like that, right? Secretly, right? You don't need to know it. You don't need to know it. But so you may not like PDs, you may not like Hamilton-Jacobi equations, you may not like all that. The models don't care, right? They do them whether you like it or not, right? Right? So this is the first thing we're going to do, right? We're going to show this connection, right? So just to give an example, right? So I have this continuous time normalizing flows. I have this ODE here. The flux is parameterized by some neural network. The initial data is, and the terminal data is this connection between target and simple distribution and complex distribution. And I want to push forward the simple distribution using this dynamics. And what does it mean to push forward? I want to push it forward towards my data, towards my target, right? So I want to take this and push it over there, right? So once I push it over there, I want to optimize, right? I want to find who is the closest. So I'm going to use Kullback-Leibler because when I took statistical mechanics, someone told me this is the best thing, and somebody else, when they took their stat classes, they like MLE and whatever, right? So they want to optimize this, but you optimize over all thetas. This is the parameters. The parameters happen at each stage here, right? So they're time dependent. And if you do some calculus, you get how does it look like in terms of the evolution of this. This here, as you know, is essentially a transport equation. So what is going on here, right? You have a transport equation, right? Method of characteristics, if you want, coupled with information theory, right? Right? PD is coupled with information theory, right? I like that, right? I like that, right? Because I'm an applied math guy that works in both, right? But in practice, this is what's going on, right? So, yeah. So you move some dynamics and you optimize something. So what kind of a problem is this? Right? What kind of optimization problem is this, right? Right? I say it's an optimal control problem, right? So in optimal control, I have dynamics, I have some initial data. I want to optimize something in time, right, in time. And maybe I have so usually I have a terminal cost, right, just like the previous problem, right? So you see in the previous problem, I don't care how I go from here to there. I only care that I arrive there, right? So terminal cost, right? So I have a terminal cost, right? And maybe have a running cost, right? In optimal control, we have running costs, right? And but one tiny little detail, tiny little detail. So it looks like an optimal control problem, but it's a tiny little detail that the initial data are sampled from the uniform distribution, right? So it's not like optimal control with many samples, right? So it looks like this, right? So I have a target. My target is this CRPC carpet, right? So my initial data is some uniform guy over here, right? And I want to land on the CRPC carpet, right? In some optimal way, right? So some later time I'm here, and if I play my cards right, I'm gonna land on it, right? When I hit my target. If I play my, right? Not obvious, right? Hopefully, right? So, right, so it is a control problem with many particles. So it's a mean field control type thing, mean field game, something like that, right? So something like that, right? So it turns out that it's exactly this. Same thing happens also, you have the same perspective, this optimal control perspective when you train transformers. And I don't want to say a lot about this, but transformers are also deep, and you can approximate with dynamics, and there's good stuff going on with this perspective, but I will say nothing because Kelvin will talk about this afternoon. Also, you can see his poster, right? And you can also see the paper here, right? So it's a similar perspective, but also very different in some ways, right? Because of the structure of the transformers, right? So, so outline of the talk, we are already here. We talked about, we gave a little primer, right, for flows. So we're kind of here. And then we also said, how do we understand mathematically? Well, there is some control theory, we said, right? And we are kind of here. So we're about to talk about Hamilton-Jacobi and meaningful games and stuff like that, right? But then the other thing that I'm really interested in, and this ongoing work with some of the wonderful collaborators, is how to do some science and engineering applications, right? Using generative modeling. One can do likelihood-free inference. Here I'm interested in doing very high dimensional control problems using designer generative models, right? So just want to emphasize this. So in my abstract, I had something about model from uncertain quantification, PD regularity theory for generated flows, score-based diffusion generative models are robust. There are multiple sources of errors. I had something like that. I won't talk about this. I want to keep the talk short. And of course, there are also other aspects about structural informed learning. I won't mention that, so we've done a lot of work on this. But we will have a real expert tomorrow talking on this, Wei Zhu, right? Talking a lot about this very important area and his work. And so shout out to him. So let's start, right? So, oh yes, and before that, I just want to acknowledge all these wonderful collaborators. And of course, the senior collaborators are great, like Stan and Luke and Paul, right? But what is really great here is the young collaborators. So, and it's such a privilege to work with them and to see them grow and to see them succeed. So Hemin is giving a talk and has a poster. Sejuan has a poster that you can see out there, and Kelvin has both a poster and a talk. And yeah, so just talking about mean field games and how they are related, how they are like a framework for generative flows. So this is work that we've done with Ben. You saw Ben's talk earlier this week on a different topic. So we'll talk about neural OD flows and diffusion-based generative models, but a lot more can be done. I'm just going to give you some examples and connect them to some equations that maybe you've seen before, right? So mean field games, right? I have this caricature you have lots of individuals, and individuals like this fish, but they interact also as individuals and as a school, right? A school of fish, right? So you have density and individuals interacting, and so you build a control problem like the one that we saw before with dynamics, maybe deterministic, maybe stochastic. It's very flexible. The dynamics can be given in terms of transport equation. So transport equations are in the background, whether it's deterministic or whether they are just first order, second order, right, like this one. And then we want to optimize a functional. We have some targets, so the functionals describe some running cost. What does it pay to go from point A to point B, right, from this to some other point? Interaction cost, these fish interact with each other, may interact with each other, right? And also there's some terminal cost. Where do you want to go? Where are you going, right? Did you reach your goal, yes or no, right? So this is a general theory, right? And a particular aspect of it is the potential mean-field games, right? You can see all that in the book in the famous paper by Lastry and Lyons. So this is a great paper, but Stan's paper gives you a much more applied math perspective that has the theory and the numerical methods, and I found that paper very important in my understanding of the field. So I highly recommend that paper. So this is the problem, interactions, running costs, right? And any optimization problem has optimality conditions. If it's well posed, right? If it's well posed, it needs to have optimality conditions. What are they? I will not prove them what they are, right? But it's easy to do the calculation. There is a system, as we've seen in previous talks, of a Hamilton-Jacobi equation and a Fokker-Planck equation. So the Fokker-Planck equation is really the control dynamics. What is the best solution here for this? What's the best V, right? I'm optimizing over V. This best V is given by the Hamiltonian on the value function, and the value function solves the Hamilton-Jacobi equation. So this, notice this. This is forward, this is backwards, right? So maybe it's a coincidence, right, that we had a forward and a backward in the first slide about generative modeling. Maybe it's a coincidence. Actually, as you know, in mathematics there are no coincidences, right? So that's the great thing about the field, right? And what is the Hamiltonian, right? So what's the Hamiltonian? This is the Hamiltonian over here, right? So that's the Hamiltonian. The Hamiltonian is associated, as you see, with the running cost, right? Running cost, right? Here, right? And of course, the velocity, the optimal velocity field, right, is given by the Hamiltonian. And the solution of the Hamilton-Jacobi equation. The interaction cost pops up over here. Look at this term, right? This term is a variational derivative, right? So it's a variational derivative of this term over here, right? If it exists, right? If it exists, right? And terminal cost enters as a terminal condition for the Hamilton-Jacobi equation, and also this thing has to exist. It's also another variational derivative. So that's going to play a big role downstream in the talk. So the variational derivatives are important. And yeah. So that is just mean-field games. So why mean-field? So we saw that we have this cloud of particles landing on the target, and it looks like an optimization problem. So now I'm going to try to make this schematic that I showed you earlier, right, with this cloud landing on the Sierpinski carpet, make it more rigorous, the connection, right? So in generative models, we train something like this, some distance from the target. Some people, like Lars, right, are adding, for very good reasons, regularization terms, right? Various groups have tried that, right? Right. So and then all this is subject to some dynamics. So this is a slide that I really like that Ben made, right? So so how does that come together with mean-field games, right? So I have here an optimization problem. I have here an optimization problem. They kind of look alike, right? They kind of look alike, right? I have dynamics. I have dynamics here, right? This is related to that, right? That's the PD version of this, right? But meaningful games have a lot more structure that we acknowledge when we're doing generative modeling. The structure is given by the optimality conditions, right? So when you do generative modeling, the algorithms don't know anything about Hamilton-Jacobi equations. As I said, you may not care about them, right? About Hamilton-Jacobi equations, you may not care about meaningful games, but they care about the algorithm, right? Because they are operating in the algorithm secretly, right? Right? So there is an optimal solution, right? The optimal solution of the generative model is given actually by the formula, right? Has some structure, right? Has some structure, right? That you don't use usually in this algorithm, but it does have a structure. The forward part is the generator generates. The backwards part, the Hamilton-Jacobi equation, identifies, right? Finds the best problem, the best solution, right? Identifies the velocity field, right? So that's the backward-forward nature that we saw in the very basic setting. It's evident here in the meaningful game correspondence to flow-based models. You see they are flow-based because there is a flow here, right? There's a flow, right? So there's a common backward-forward structure. The backward equation derives the optimal velocity field, the Hamilton-Jacobi equation, right? And the forward is the generation, right? And applies to all flow and diffusion-based models, right? So just some examples of known things, right? So I'm going to do two known things, and then I'm going to do something that is not known, right? So the first example is, we talked about normalizing flows. Let's see what's the connection between meaningful games. What is a meaningful game that goes with us, right? So it's kind of known. It's known, right? It's known that the continuous normalizing flows of that type are unstable, right? They're difficult to train. They blow up, right? And why is that? Intuitively, you can think of this. This is a control problem. I have to go from here to there. I can go in a straight line, or I can wiggle. I can also you can construct examples where you get impulsive controls. Impulsive controls have direct masses, right? So you can have widely oscillating objects, right? And all of them are good. All of them are solutions, right? That is captured here by what I just said, right, in words, right, is captured here by the optimality conditions, right? So if you try, so this is my mean field game. There is no interaction, right? Just this, right? Just optimizing this. There is no interaction. There's no running cost. This is what I want to optimize, so I might as well go through the crank of mean field games and write down the optimality conditions. Optimality conditions have Hamiltonian, right? Hamiltonian, here's Hamiltonian, there is no L. There is no L here, right? Take the soup of this, see the zero on infinity. Good luck with that Hamiltonian, right? No Hamiltonian, right? Yeah, right. So it checks with our intuition, right? How to fix it? I have a fixed number one, right? Fixed number one. So how about if you put a bound on the velocity, right? Bounds on the velocity are always good, right? Because I'm always thinking, I was trained in PDEs, right? So I'm always thinking CFL conditions and stuff like that, right? So bounds on the velocity are good. So I'm just going to put a bound on the velocity, see what happens, right? The Hamiltonian, look at the Hamiltonian, right? I'm going to optimize here, right? And the Hamiltonian looks like this. Now, that's a Hamiltonian that Stan knows very well because this Hamilton-Jacobi equation is a level set equation that Stan introduced as a foundational method for front propagation. First order and second order, right? And other stuff. So here what happens is that look at this mean field game. It has a front propagation level set equation, right? That came from here. The speed is the maximum speed, right? The maximum speed, right? Of the front. This is the transport equation, right? This optimal velocity field. And this is the terminal condition, which is the variation of that, right? The variation of that, right? the variation of that. So we'll go back to that, we'll examine that later, right? But let me just move on now to another. So this regularization is not the only one. You can do many, and you can see some discussion of this regularization maybe in Kelvin's talk. I don't know how deep you're going to go to the newer stuff in the talk, but there are many different regularizations. But here's one that I really liked, introduced by Lars and his collaborators in this wonderful paper that I highly recommend for you to read, because there are many different interesting layers here, mathematical and computational. And so look at this object. So this is like an optimal transport term, right? So in Luke's talk, we saw something like this, and Luke called these types of divergences proximal OT divergences, right? It's a class of divergences that look like this. So that's the divergence itself, it turns out, as Luke showed us, right? So you have this regularization over here, which is it's a kinetic energy, right? So you see the previous regularization put a maximum speed, right? Speed limit. This one penalizes the integral, right? The kinetic energy, right? So I'm going to do optimality conditions. Now that's something that you've seen before, right? We saw in various talks here, right? So the Hamiltonian, you know what it is. It's the Eikonal equation, right? Optimal velocity field, here it is, right? So that's that, and the variational derivatives here, right? So Lars and his team, they use this to improve the performance of normalizing flows, right? Right, so different type, right? Just option 1, level state equation, option 2, Eikonal equation, right? Not unique, right? And so in various papers, right, we can show that because of the method of characteristics, right, the transport is done along straight lines, right, and you get some uniqueness, right? Yeah. So that's example 1, right? Example 1. Now you may be asking yourself, what happens with score, right? Score is our favorite. Is it our favorite method? One of our favorite methods, right? Score, right? All of we like them all, right? Yeah. So what happens here, right? So we saw a little bit of that in Sitting's talk, right? But let me view it from a mean-field game point of view, right? So score-based methods have a noising and denoising process. They are stochastic, and you go forward in this. So this is some dynamics. That's the general calculation. The F could be anything, not in the method, right? But in principle. But then you can reverse it exactly if you know the score. The score is this object over here, right? If you know the score, you can reverse. You can solve the heat equation backwards, right? It's a big no-no if you take PDE classes, graduate PDE classes, and numerical methods, right? It's a big no-no. You're not allowed to do that, right? Because the problem is unstable. But if you know the score, well, you can do it, right? You can do it, right? So and that's a very deep insight, right? And that in these wonderful papers by Song and Ermon and all these people. And if you learn the score through score matching, this is great, right? You can do all this the dog here, right? That everybody has, right? So is there a mean-field game going on? There's a claim here. SGMs are as a mean-field game, right? So how do they look like? Well, they have some familiar terms, right? So there is a cross-entropy term, right? There is an optimal transport term, and there is another cost that's associated with F, right? Divergence of F, right? So it's not exactly optimal transport unless F is 0, right? So we saw that in Sitting's talk, right? So it turns out that this is the mean-field game associated with that. And one of the things that you realize is that there's always a Hamilton-Jacobi equation hiding someplace. Hiding, right? Hiding. Although they're always hiding someplace, right? Right, so the optimality conditions look like this, right? That's the Hamilton-Jacobi equation, backwards, right? You do variational derivative and you get log of pi, the target, right? If you do Kohl-Hopf, right? So I learned Kohl-Hopf from my co-advisor, Wendell Fleming, right? Who was using these types of ideas to study large deviations problems, right? And viscous solutions, right? So, so you do cold hop here, right? And you get this system, and that's exactly the system, the forward and the reverse, right? With the score, right? With the score, right? So the score pops up over here, right? It's kind of a miracle calculation, right? Right? So, right? So that is a, so the forward SD, right? The forward SD, this guy here, is actually Hamilton-Jacobi equation through cold hop, right? And yeah, so it's a surprising fact. So if you just want to put everything that we saw up to now together in one big box, right? In this OT flow, right? Optimal, this normalizing flow with optimal transport regularization, we have a terminal cost. Here, this is KL, but for SGMs, it is cross entropy, right? This is called cross entropy, right? There is no interaction cost, at least for SDs, right? And the dynamics is deterministic, here is stochastic, right? Now, if you are curious about the, if you're interaction curious, right? If you're interaction curious, and you ask me, do you know of an example that has an interaction? I say yes, right? So if you look at, so SGMs can be implemented through something called probability flow, right? So if you want the probability flow situation, you don't have stochastics here, right? So that is replaced with an interaction term that is, which is Fisher information. So Fisher information replaces the like this, right? So it's an interesting calculation. It's in the paper with Ben, right? So just again to compare them, right? OT normalizing flow versus score. Look what happens here, right? So this system, right, is fully coupled, right? Look at this, it's fully coupled. So this and that, they talk to each other, right? Because U is here, rho is there, right? But also they are coupled to the terminal condition, right? The terminal condition of this guy involves rho, right? So they're coupled. Now look what happens with score. There's some miracle that happened. The Hamilton-Jacobi equation is fully decoupled because the terminal condition has just the data, log pi. So in principle, you can solve this first, and you can solve this second. So these two guys are decoupled. So score decouples the two, right? Right? So it has that miracle, that miraculous simplification that we also know from we know from the actual implementation. We do this first and we do this second. So we learn something from here and we use it there, right? So that's how the algorithm works, and you see that in the optimality condition. So this little miracle, right? So I just want to so now, okay, so we talked about exhibit A, exhibit B, right? Some stuff that we know, how they mess together with midfield games, right? So just something, I just want to also say something new, right? So if I go back to this OT regularization, look what happens. If you look at, so for these equations, for this system to be well posed, it's not enough just the Hamilton-Jacobi to be good. Also right? You know this from PDEs, right? Your terminal conditions, your boundary conditions, everything has to be right. Not enough, right? Not enough. So when you solve a PDE, you have to take care of everything, right? And look at the terminal condition here, right? This is the fact, because this is KL, right? So I have this ratio. And the ratio is a very dangerous animal, right? Because if pi of x is singular, right? If pi of x lives on a manifold, right? Good luck with that. This is going to blow up. And you see that very well in Lars's paper, where he's using autoencoders, right? For larger systems, right? Yeah. Right. So that's why. So this is good. This is good, right? We fixed that, but we have not fixed that yet. We have not fixed the terminal condition of Hamilton-Jacobi yet. So if you're asking why Hamilton-Jacobi equations are important, it's not because we use them to solve anything, because in higher dimensions you cannot, right? With grid methods, right? But because it can guide us in algorithms. So this is an example of guidance. So I should not be using this, right? Right? So instead of when I use this divergence, that we saw in the talk by Luke, this divergence, which is the Wasserstein one, this Lipschitz regularized divergence, Kullback-Leibler, right? So it is proximal of Kullback-Leibler with W1, Wasserstein 1. So it has this dual form. So as soon as I have this dual form, I know that I'm in business. I can do this, right? Because I can use neural nets for that. There's a Lipschitz constraint. I know how to impose Lipschitz constraints in neural networks, right? I know how to do that. There's software for that in PyTorch, right? And so these types of divergences were introduced in an earlier paper by Jeremy Birrell, our former postdoc, in this JMLR paper. And the great thing about them is that this variable derivative is always defined, always well defined, always, right? Always. And you'll see what I mean by always in the next slide, right? So these variable derivatives, right, will make, so also they are well defined, and this optimal guy, right, optimal guy, he's actually equal to the variable derivative, so I'm going to be solving this system. It's going to be always well posed. So this new divergence allows you to compare two things, right? That's two things. Allows you to compare singular objects, and is smooth. And the smoothness is inherited by KL, right? So, so these types of variable derivatives are important in general, right? Because whenever, because when you optimize over parameter space, they pop up, right? Theoretically, they pop up with this formal calculation, right? So, so we have this result with Ziyu Chen, who was a postdoc at UMass, and now he's starting as a assistant professor at UNC Chapel Hill, and Hemin, who's going to be giving a talk later. So you can prove that this variable derivative always exists. Remember, we need it for the optimality condition, right? So it always exists. The only condition is that this P here has to have a mean, right? A mean. That's not a lot, right? A mean. And pi could be anything. And because of that, because of this ability to handle any target, you can do heavy tails, as we saw in Luke's talk yesterday, but also you can land on weird things like this attractor, right? Look how well it lands with the attractor, right, of a Lorentz 53. Yeah. So yeah. So in this paper here, we implemented that, right, which is with other collaborators. If you have if you don't regularize the KL, right, you can blow up terminal, right? Terminal cost blows up. You are much more smooth, right? You are much more smooth. This is the kinetic energy, right? Because the solution of the trajectories are straight lines, also, right? So the kinetic energy is lower and much smoother, right? It's a manifestation of the straight line optimal trajectories. And if you want, again, no specialized architectures, right? So, let me go back. Yes. So key point which I want to say here is that we don't, to get this is an MNIST calculation, you don't have any specialized architectures, no autoencoders, right? Everything is very stable. And you can see that here in this baby calculation, right? So this is a pinwheel, right, in 2D. So this is with KL, this is with Lipschitz regularized. They're done okay, right? Both of them can handle it. But as soon as you go to high, so now we embed this into this plane, we embed this into a 7D space, right? So it's a very low dimensional. And immediately KL breaks, right? Because it doesn't like singular stuff. Well, this guy can handle it. 12D can handle it, right? And the other thing I want to say is just a remark that we're exploring right now is that also because of this dual formulation of this KL, basically you have an adversarial formulation of this normalizing flow. So it's a gun. It's a gun, right? But it's a gun. So guns are very unstable, as all of you know, right? And if you have lots of layers, if you have few layers, good. If you have lots of layers, not good. These are super stable guns, right? So it's something that's an ongoing works, and it seems that this stabilizes things. We also have different terms here, as we found out with Kelvin, right? And yeah, so maybe I have, I'm out of time, or?
Yes, but
I'll say one thing.
Yeah, sure.
I'll say one thing, right? One thing. So one of the main directions that we're interested in is to build designer generative flows for optimal control in very high dimensions, right? So they're designed for specific things, right? So far we saw that mean-field games are a mathematical framework for generative flows, but I want to reverse, right? I want to use generative flows to solve high-dimensional control problems, right? So here's an example of a problem. You have lots of agents, drones, that want to go to a specific target. Maybe they're delivering pizzas, maybe they're delivering, I don't know what they're delivering, right? Right, on a target, right? They interact, they want to land on the target. And what does it mean to land on the target? Means that one way to do this is to have some sort of soft penalization. This has to land on that. How to land on very singular targets, right? You have to use, again, the same divergence that we saw a second ago, right? Of course, you have interactions, you have other terms, right? So here's an example, right? I'm going to finish with this. So here's an example. I want to land on this very high-dimensional object, on these high dimensions on these two wires, right? These two wires, right? So that's a very tiny, thin target, very singular target. I want to land my agents on that, right? Well, this guy lands it, KL does not, of course, right? Does not. So, yeah, so this is one of our ongoing projects. There are many other applications, right? Many other applications of generative modeling, likelihood-free inference. I didn't talk about this. Lots of work on this by lots of people. Also work on fine-tuning and transferability. You can see the Janis poster out there. Don't discuss it here, right? And some papers.